Morning, everyone. Let's get started. We are going to be working on finishing off the area between two curves and hopefully getting an intro to the next section, 6.2, which is to do with volumes. Well, we already yesterday looked at the area between two curves when it was, y is a function of x kind of thing. What we're going to look at now is the other direction. So can you see that in this case, the orientation is kind of left to right? And the reason for that is that these two curves are not y equals x cubed or y equals 2x plus 1. These are x equals a function of y. So these are things like x equals y cubed plus y and x equals y cubed minus 4, those kind of things. So how do you find the area between two curves when they're orientated this way, left to right? Well, the good news is you pretty much do what you would have done anyway. The formula for the area between these two curves is the integral from the y value where it starts, which is c, to the y value where it ends, which is d. And the formula is f of y take away g of y. Can you remember when we did the x's? The top guy was f of x and the bottom guy, the one below it, was the g of x. Remember, that's how we decided which way around to do them. When you do it in this orientation, the one that's furthest to the right is always going to be f of y, right? So the function that's furthest to the right is going to be your f of y. As long as you get that, you're fine. So let's look at some examples of it. Here is one of those questions where we're being asked to find the area between the red and the green curve. And a lot of what you need is kind of given to you. So what we're going to do now is finish it off. So I know you probably can't read it, but that number there is y is -1 and this one up here is +1. So I know the start and finish. So the area between these two curves is going to be the integral from y is -1 to y is 1. And then it's going to be f of y take away g of y dy. Okay, which one of these two curves, the red one or the green one, is going to be f of y?
E to the y.
Okay, the red one, e to the y. Take away y squared, take away 8 dy. Are we comfortable about how that was set up? Where the numbers came from, why we picked the f of y and why we picked who was going to be the g of y? Are we comfortable about the setup? So if you were given this picture, would you be able to create this? And if the answer is yes, then we're good. Now, this will become e to the y, take away y squared plus 8. And for the most part, the integration is not that messy. E to the y gets you that guy. Power rule for the middle one. And technically it's a power rule for the last one. And it goes from -1 to 1. Nothing too remarkable about that, right? E to the y is just e to the y when you integrate it. Let's plug in some numbers, see what we get. You get e to the 1, take away 1/3 times 1 squared, 8 times 1, subtract e to the -1. You plug in -1 here, you'll get -1/3. You plug -1 in here, you get -8. What do I get? I get e, I get this guy, I got this guy. Take away e to the -1, which I'm going to write like that. Take away a negative means I add that. Take away a negative means I add that. So what's left? I've got an e, I've got -1 over e, and I've got +16. And we are finished. Are we good with that? Right. I think if you can get to this line here, well, maybe this one. If you can get to this line here, isn't the rest pretty standard? It's just find integrals. Doesn't really matter where the integral came from, you're still going to do what you need to do. And style points, you know, E rather than E to the 1, not really that much in the way of style points either. Okay, that was 3 done. Oh, shouldn't have done that. Never mind. I can fix it. Here's the next one. 4. Okay, what would be the limits of integration, the numbers that go here and here, based on what you can see in that picture? What goes in the bottom? It's not meant to be a trick question.
Got
0 and 5.
There. 0 and then 5. Agreed. Now we should be doing f of y. Okay, take away g of y, which we will. D of y. Okay, red or green? Which one is going to be f of y?
Red.
Right, this guy. So it's going to be 4y take away y squared, subtract y squared, take away 6y. So it's going to be the integral from 0 to 5. 4y take away negative is added, so you get 10y. Negative y squared, take away another one, gets you negative 2y squared dy. At this point, can I do the dot, dot, dot? Would you agree you should be able to integrate that without too much trouble? Suppose I got the answer -5, negative 5. Why should I be worried?
It's not a net value. These should all be positive.
Right? So if you don't get an area, because these are actually physical areas, right? These are not areas under curves that are allowed to be negative, right? Or net areas, as you call them, right? Which is a good name for them. These are physical areas in real two-dimensional space, but they're still physical, so they need to be positive. One of the mistakes that I can sometimes make quite easily is if you get the F and G the wrong way around, your answer will be negative. The number that it's equal to will be the right number. You'll just get -10 when it should have been +10. So if you're doing a homework question, especially if it's a really long one, and you get -10, you know it's wrong, right? Because it's negative. Well, you try putting in 10, and if the answer is correct, all that meant is that you got your F and G back to front. And it saves you having to do the whole question from scratch, right? Are we good with that? Okay. Our next one that we're going to have a look at, I believe, put my little list here, is 12. 12 is different because you don't get all the stuff that you need. We're going to have to use Desmos to help us. Essentially, I'm going to use this piece of information to draw that picture, right? So we're going to use this on Desmos to see what it looks like. So let's see what that becomes. I should have Desmos set up. I just need to find out where it is. Here it is. Are you looking at Desmos right now? Okay, so if I type in, darn it, I need an extra table or longer arms. There we go. X equals 4 take away y squared. That was the first function. And then the other one was x equals y squared minus 4. And there was the second function. Oh, that came out quite nice. It's, would you agree you can see the area they're talking about is this, looks like an egg, isn't it? Now, would you agree that the intersection points are at y equals -2 and at +2? You agree? So although you can't see it, I'm writing that down. I'm doing the integral from -2 to 2. Now, red guy or blue guy? Which one of them is the f of y?
Red guy.
Right? One's to the right, the red guy in this case. So that's going to be 4 take away y squared, subtract y squared take away 4 dy. So from that picture, we managed to get everything that we need to set up the integral for the area between those two curves. And it's that guy. Are you happy about the -2 to 2 that we had a few moments ago? The f of y take away, that was the g of y. We already agreed on that. This is now going to be the integral from -2 to 2. And what do you get? 4 take away -4 is 8. That guy and that guy. I'm getting deja vu here. You got that guy. And then dot, dot, dot. You're done. Okay. I believe we have another one in my little list. Here is question 15. This is going to be the last one of this type. So I'm going to find out what the area between these two curves are going to be. And so that means I need to go back to my Desmos and set it all up. So make that one go away, make that one go away. And the first one was x equals 5y squared. And the second function was x equals 16 plus y squared. And when I look at that, it looks like, oh, we got a problem. I can only see one curve, the green one. So I'm going to shrink it out and move it along. Can you see it now? So the bit that we're looking for is basically here. I know it looks like a rocket, doesn't it? Kind of side on. Okay. So let's set up the integral that would give me the area between the purple and the green, right? This area here. Okay. Limits of integration, right? If you click on that intersection point, if I can click on it, there we go. Do you see that it has a y coordinate of -2, which you can read pretty clearly? And this guy up here is 2. So the limits are from y equals -2 to y equals +2, right? Y equals -2 to y equals +2. The purple guy or the green guy, who goes first? Purple guy or green guy?
Purple.
Right, so 16 plus y squared. Are you getting comfortable with the guy to the right is f of y? Right, the one that's furthest to the right is the f of y. And that is pretty much everything that you need to set up this integral. So that's what I'm going to do. It was from -2 to 2. The guy to the right, take away the guy to the left. That becomes from -2 to 2. 16, take away 4y squared. And, you know, off you go, finish it off. In a lot of ways, isn't the y ones, the left-right orientation, and the x's were like the up-down orientation, aren't they mathematically very similar? Right, they have a lot of overlap. So if you can know how to do one, you should be able to figure out how to do the other. Are we good? Right. So let's show you what is like the leftovers, things that we haven't covered yet in that section. Not that much. So let me show you what we're still to do, and then we can get on with the volumes, which is a new topic. Okay, it's this guy. In question 16, Do you notice that the information, why is that doing that all the time now? What on earth are you doing? I can't click on this. It's when I click on it, it does that. I have no idea why. Okay. Without me clicking then, because it'll disappear on me. There we go. Right. Do you see this guy here? What's wrong with the information is that it's not given to us as y equals a function of x. At least the second one isn't. You see it's given as x minus y equals 3. Now, if you do a quick rearrangement, can you trust me that's y equals x minus 3? And when you do it in Desmos, and you do the square root guy, which looks like this fella, and the straight line guy, which looks like that, it ends up being this picture. Does that make sense? And can't you then set up the limits of integration? Oh, by the way, isn't this the one, the up-down version? Right, the x's version. Okay. And the other stuff is just stuff we covered yesterday, so I'm not going to spend any time on those. And I think that's it. Yeah, that's it. So if I gave you two curves and I said I want to know the area between them, hopefully you should be able to figure out how to do it. That's pretty much what these were all about. So we are now going to move on. And I'm going to do this by note. So you are all about to see why I am, well, not why I am, but that I am a very bad drawer. Which is kind of strange because I'm quite a visual learner. In other words, I can see, in many cases anyway, I can see what it is. I can imagine it in my brain. And I move my hands around as if it's there sometimes. You might see me going like this and wondering what I'm doing. I can visualize it quite well. I just can't draw. Just useless, bad artist. Which is a bit of a problem because if I was a good artist, this will be a lot clearer. So you're just going to have to forgive me for the fact I can't draw well. We are going to look at section 6.2, volumes. Actually, its full title should be Volumes of Revolution. And we don't mean revolution like French Revolution. We mean revolution meaning turning, revolving. So here's the problem. We imagine that we have a curve, and this curve is going to look like that, and it's going to be our classic y equals f of x. And it's going to start at A, and it's going to finish at B. But what we're going to do is we're going to rotate this curve about the x-axis. Now, can you imagine if you rotated this curve about the x-axis, wouldn't you make a solid shape? It would look a bit like a vase or something. Now, this is the bit that I'm not good at, but I'll try my best. Not bad. Can you imagine what that would look like as it turns around? Now, if I put a little bit of artistic license on it, do you get a feel for the shape of that solid? I'm actually impressed by myself. That's a lot better than most of my 3D pictures look. Our job is to find the volume of that solid shape. It's called the volume of revolution. So if you imagine, as long as the curve's above the x-axis and you rotate it about the x-axis, won't you make some kind of weird 3D shape? And we're going to find the volume of that weird 3D shape. This is not that. Actually, do you know what that reminds me of? A bell, a solid bell. Right. So how do we do it? Well, let me do the magic and then I'll try and prove the magic. the volume of this shape, called the volume of revolution, is an integral. That's a surprise for you. Because don't integrals normally get you areas of things? You don't expect it to get you volumes of things, but it does. And it's the integral from the start number to the finish, from A to B. That's not too surprising. Pi, whatever the function is, squared dx. I think the first thing is how remarkably simple the formula is. I mean, you might have expected it to be a lot weirder, but it's not. It's just pi times the function squared dx. So I'm going to try and prove to you where this formula comes from. It's not a perfect proof, but it kind of works. So this is really only for the benefit of those people who do not like magic, how you could come up with this formula. So I'm going to do my A to B thing again. Okay. So imagine this shape here, right? Now, choose a random piece and call it X, or a random guy there, call it X. And then another guy, delta X. So basically, can you imagine me cutting this with a saw? That strip, right? Now, if I cut that thing, that strip, wouldn't you get a little thin, looks like a coaster that you put glasses on top of? Wouldn't it be a very thin little circle, right? With a little thickness. Now, right, so you imagine this cut this way. Can you look at it that way? Wouldn't you see a little circle? Actually, it's a little cylinder. Wouldn't that distance be delta X? And this distance from here to here is the radius, right? Now I can find the volume of one of these little strip things, right? These little discs. The volume of this little disc is pi times r squared times h. Let's try and make sure I use that. Remember the volume of a cylinder, pi r squared h? Now, in this case, isn't h delta x? Now, the radius is the distance from there to there. Isn't the radius the distance from here to here then? Isn't that my radius? Well, wait a minute. Isn't that distance actually the value of the function x? Now, that guy is him. Because essentially you cut the whole shape into lots of little strips and you add them up and you make it go infinite and do all sorts of stuff. But can you get the basic structure of where that pi f of x squared is coming from? And the delta x is basically like that little guy. So far, so good? Right, let's put that into action then. Let's actually find the volume of a shape. Let's find the volume of the shape y equals x squared, starting at 1 and finishing at 2. So can you imagine I rotated that shape about the x-axis? So what would that look like? One, go here, 1, 2, 3, here. So we would look, it would look something like this. Okay, not the, you get a vague idea of what the solid shape looks like, even if I can't draw it well. We would like to know the volume of that shape. Well, it's going to be the integral from start to finish, so that's 1 to 2, pi f of x squared. I tend to bring out the pi, and I go from 1 to 2. And this fella here is x squared. So basically x squared squared. That becomes pi, the integral from 1 to 2 of x to the 4. And that becomes 1/5 x to the 5, x equals 1 to x equals 2. So far, so good. If you plug in 2, you get 2, 4, 8, 16, 32 fifths. Take away 1/5. So the final answer is 31/5 pi. So the volume of that thing is 31/5 pi. And we did it by using the integration formula to find its volume. Is there anything about that that's unclear that you'd like me to explain? It's quite powerful, isn't it? I mean, how else could you get a volume of a weird looking shape like that? You know, if we didn't have this trick, this volume of revolution trick. Okay. I'm going to prove something to you which seems obvious, but hard to prove. Let's suppose I've got a circle whose radius is 4. Right? Imagine a circle whose radius is 4. Right? Now, if you take a circle whose radius is 4 and you rotate it, right, about the x-axis, right, don't you end up with a sphere? Would that make sense? If you took a circle and rotated it about the x-axis. So can you imagine that I took, well, actually, I'd only need the top half of the circle, wouldn't you? Because when you rotate it, you get the bottom half for free. Wouldn't this shape rotated about the x-axis give me a sphere of radius 4? So far, so good. Now, does anybody here know what the volume of a sphere is? Unfair to ask you because I don't think you've used it much, if at all, lately. Just anybody know it before I tell you?
4/3 pi r cubed.
Well done. Yes. Now, if you take a circle whose radius is 4, then what you would expect then, right, would be x squared plus y squared equals 4 squared. And wouldn't that get you y squared is 16 take away x squared? And wouldn't that get you technically plus or minus, but if I only want the top half, isn't that the equation of the top half of a circle? Are you comfortable about where I got that from? I know that is not 4 minus x. You can't do square root calculations that way. So I now have the square root of 16 minus x squared. And this guy is 4. And this guy is -4. We're still good? Well, if you take this shape and you find its volume, it's going to be the integral from -4 to 4 pi, the function, squared dx. If you pull out the pi, if you square a square root, you get that guy. That gets you pi, 16x, take away 1/3 x cubed, evaluated at these two. That's pi, 16 times 4, take away 1/3 times 4 cubed, minus 16 times -4, take away 1/3 -4 cubed, and I'm shooting through this. That's going to be pi. That's 64, take away 64 thirds. negative 64, add 64 thirds. And that gets us 128. And this guy, take away that guy, gets you negative 128 thirds. So basically you're getting pi times 2/3 of 128. Now I could actually calculate that, but I'm going to leave it a little bit closer to that value. And I'm just going to pull out a 2. And if you pull out a 2, you get that. And then isn't 64 4 cubed? Aren't we looking at the formula 4/3 pi radius cubed? You see, we've actually found the volume of a sphere without needing to use 4/3 pi r cubed. Couldn't I do it for a radius 10 or a radius 20? And in fact, I could do, instead of calling that 4, couldn't I have called that r? And I would have ended up with 4/3 pi r cubed. I have just created the formula for the volume of a sphere from scratch. That's pretty impressive. I can find the volume of all sorts of things. You know, the volume of a cylinder is pi r squared h. Agreed? We've got time. Do you want to see a proof that that's the formula for the volume of a cylinder? Let's do it. Shows you the power of calculus. Right, I want to get a cylinder, right? The first thing I'm going to do is just put the cylinder side on. And I'm going to make that distance, right, h, right? This distance is r, right? And right around the center of it, right? Right down there is going to be where my x-axis of rotation is. So if I want to make a cylinder happen, all I need to do is have a line that looks like that. And that line happens to have the equation y equals r. Would you agree? If that's r, that line is y equals r. And I'm going to start at 0, and I'm going to finish at h. If you rotate this shape, if you rotate it about the x-axis, won't you make a cylinder whose radius is r and whose height is h? Right? So according to the formula that we have, it should be the integral from 0 to h, pi times the function f of x squared dx. So it's integral from 0 to h of pi. Well, when you say y equals r, aren't you just also saying f of x equals r, which is the same thing? So what we have is r squared dx. Isn't pi a constant and r is a constant? So that's a bit like 5. So when you integrate it, you get pi r squared x evaluated at x equals 0 to x equals h. And that gets you pi r squared h, take away nothing. We have just proved that the volume of a cylinder is pi r squared h. You can take pretty much any of the obvious shapes that we have formulas for, right? Like the formula of a cone, or the formula for a sphere, or the formula for a cylinder, and create them from scratch. So if you wondered, where did those formulas come from? Because you were just told, hey, guys, you want the volume of a sphere, it's 4/3 pi r squared, pi r cubed. Right, we just told you. Can you see where it came from? It came from calculus. Somebody says, I want to know what the volume of a cylinder is. So all you do is you set up a nice picture of something that you can rotate about the x-axis that gives you the thing you're trying to get the volume for. Make it nice and general, right? Call the radius r, call the height h, so that you've got a totally generic formula. And boom, you've got the answer to pretty much any reasonably simple shape that you could think of. That's pretty cool that you can now do that. I think it's pretty cool. Excuse me. Where am I going with this one? One last one. I'm looking for my black pen. I guess this will do. There is a very weird function, y equals the square root of x. It has problems when the sign of x is negative, but as long as I keep from 0 to pi, it's fine. Since I've closed off my other guy, I'm going to have to do this the other way. I'm just going to go square root of sine of x. I just want to see what it looks like. I'm going to do the window from 0 to pi. I'll do a zoom to fit. Oh, it's pretty boring. Kind of looks like that, doesn't it? I want to find the volume of this shape when you rotate it about the x-axis. So if I did rotate it about the x-axis, wouldn't it look a bit like an egg? Its volume then is the integral from 0 to pi f of x squared. And that's going to be the integral from 0 to pi of pi, the square root of sine x squared, which is the integral from 0 to pi, I stick the pi outside, of just sine x. Okay, be careful. What is the antiderivative of sine x?
Negative cosine x.
Okay, so negative cosine x evaluated at 0 and evaluated at pi. So it's going to be negative the cosine of pi, take away negative the cosine of 0. Okay, a lot of negatives floating about here, so I should be careful. Isn't the cosine of pi -1, so the negative of -1 is 1. The cosine of 0 is 1, but negative that is negative, and two negatives make a plus 1. And it's a very elegant answer. The volume of that shape that I just created is just 2 pi. Will you say your last name space your first name? While you're doing that, I have already sent out report 2. So if you go looking for it. If you don't get it, shoot me an email with in the email, put the address that you want me to use, and I will update my spreadsheet and I'll send you out your report. Check